Yeah, we can start.
Okay, need one second. All right, go ahead.
It's the questions that you ready then. Question is Jim ready? Okay, welcome everybody. So today we have the pleasure of welcoming Jim Burge, Professor Emeritus here in Optical Sciences and also in astronomy, but not important. He's an expert in optomechanics, optomechanical engineering, as well as precision metrology of both large and small optics. And fortunately, he's going to talk a lot about his career and life, so I don't have to during the introduction. So thanks, Jim, and take it away.
Okay. So thank you for that introduction. Thank you to the college here for inviting me to come speak
Jim, I'm
to you.
so sorry, Stephanie. Can you make sure the green light is on my camera?
Green light.
If not, just that little switch on top.
For that.
There we go. Thank you.
Okay. Okay. Once again, thanks everybody. I'm Jim Burge. I spent a lot of time here at University of Arizona, and I'm going to tell you about kind of my story. Okay, a little bit about my background, my time here, things that I've done, things that I think you'll find interesting, and we'll see. You can tell me at the end if you found them interesting. So just a couple of weeks ago, I turned 60 years old, which for me is a milestone. I know lots of people are older. I'm not claiming that prize for the oldest, but so I stop and think, you know, how do I measure up? I'm a precision metrology guy. And maybe I want to turn this on. So what size box do I fit in? Well, as a little guy, I fit in a little box, okay? Some years later, I think I go into a monumental box, okay? The statuesque woman there is my wife, Laura. So I came from Ohio. I grew up in Cincinnati and I went to Ohio State University, and this shows the campus there. You see the thing that shows up is the Horseshoe Stadium. I lived in the Horseshoe Stadium there at Ohio State. I studied physics and mechanical engineering, which is a perfect blend for me because I got to learn things that I was interested in, and it enabled me to launch off into this career that I'm going to tell you about that I like. I think it was pretty good. While I was a student, I worked at this company, which is over here, called Battelle Memorial Institute. Okay, and they did a bunch of things, but they had a group there that made these optical systems on platforms that would go into aircraft or go different places for measuring things for defense. And so some of these things were integrated in ballistic missile tests that splashed down in Kwajalein in the South Pacific. We make an optical system that we put into like a mobile mini. We take it out to South Pacific and track this thing and measure its spectra. I did this stuff as a mechanical engineer, and I was part of this team that really showed me the value and the importance of working closely together with a team of people with a common mission, with something that's really hard. That's something that just resonated with me through my life, something I just love. There's nothing that's better than that. And my first publication came from there. This is one of the old SPIE papers that was literally typed out because word processors were not yet a thing, on optomechanical design for precision pointing and tracking systems. And this was my first published air budget, of which I have done a lot. Okay, a big part of precision metrology of measuring things is knowing how good your measurement is. How good is your measurement? Usually it's as good as you can defend by looking at all the things that might go wrong with it and adding them up. While I was in Ohio, I got a love for sailing. I had a little Capri 14-foot sailboat, and on weekends I would sail that thing all over these tiny little lakes in Ohio, and that was great fun. The other thing I did is I read about the bigger world. read about sailing throughout the world. And this is a book that captivated young Jim, which is by Herman Melville. It's called Type P. And this is one of his first books, long before Moby Dick, where he actually, when he was a young man, he worked on a whaling ship and he jumped ship on the island of Nukuhiva and lived with the natives there in this valley of Typee. And his book talks about life with these native people who lived a very different life than what we have, in a part of the world that's very different than Ohio. And so this just captivated me. And working at Battelle, I learned about this magical place where I could learn optics. I was a mechanical engineer doing optical stuff, and I didn't know optics. They told me about the University of Arizona and the Optical Sciences Center. So I packed up all my things. I bought this old black van and packed all of my stuff either in it or on it. And my wife and I drove out here in 1988 for me to start graduate school so I can learn optics, because I wanted to know more about these things that the mechanics were connecting to. And this is pretty close to what the building looked like when I came. There was construction on the new wing, which is on this side, okay, the East Wing. But I didn't actually work in this building. I worked in the infrared annex with Bill Wolf. And then it was the second year that I was here, I actually moved into the regular building. But the stories of the University of Arizona coming from my colleagues at Battelle were really that there are these people there that I can learn from who really understand the fundamentals. And I was doing infrared stuff as a mechanical engineer. If you want to learn about this, what do? You pick up a book. The book is the Infrared Handbook written by Bill Wolf. So I came here and I studied under Bill Wolf. It was like a dream come true. And then I went one step beyond that and I got into telescopes. So Bill Wolf, if you know the game here, the funding goes up and down. He didn't have funding for me for a summer, so I had to go find something else. So I got a job with Roger Angel working on telescope stuff. And that got me into this really cool part of my career where I was able to work on really a fantastic evolution of mirrors for telescopes. And I'll tell you more about that here in a little bit. But it starts from, this is the Vatican Advanced Technology Telescope primary mirror, which was a giant mirror. It's 6 feet across. Okay, that was my first project, was working on that. That was, the plans were to build a telescope they called the Columbus telescope, which had two 8-meter primary mirrors, two 8-meter telescopes together. That ended up being the Large Binocular Telescope that's now built on Mount Graham. And then the current telescope that's being built at University of Arizona is the Giant Magellan Telescope. And I'll talk about all those things. So why big telescopes? Well, they're big and they're cool, right? Well, yes, that's true. But bigger telescopes let you see more. Because of the diffraction limit, you can see smaller things, so you can see sharper images. And for astronomy, a big part of it isn't just the diffraction. It's not the resolution, it's the sensitivity. So as you collect more area, you're getting more light and you're putting it into a smaller region. And so the things you can do with the Giant Magellan Telescope, you could never do with a smaller telescope because the exposures would be too long. So there's good reason for wanting bigger telescopes. Just a second, sorry. And there's a long evolution of getting bigger telescopes. And so the early telescopes, the mirrors were made of metal. Metal's shiny. It's an obvious thing to make mirrors from. It's not very stable. People later on figured out, well, you can make mirrors from glass, but it's not very reflective. So you put a thin layer of metal on top of that. The metal reflects the light, but the glass gives you the stability. And so the Mount Wilson 100-inch is a telescope that's like that. Before I came to University of Arizona, the MMT was built, which has 6 telescopes, each one of which are 1.6 meters, 1.8 meters in diameter, and they're all in a common frame. They all point together. That was called the multiple mirror telescope. That gets more collecting area. And I mentioned the LBT that I worked on, and the next one will be the GMT. But so as these telescopes get bigger, you can see their aspect is changing. The Herschel telescope is long and skinny. Okay, this telescope, the mirror is only this big, and this is as long as bigger than your house. Okay, Wilson's a little shorter. MMT, you can't see it, it's shorter. LBT is relatively shorter. That's a natural thing that you have to do. You can't just make your telescope bigger in all dimensions. If you want a bigger area, you have to make the distance, the length, the ratio of the length to the diameter smaller, or things blow up. And a challenge for making a big telescope are the big optics. The biggest optic is the primary mirror. It's the big dish-shaped thing that collects all the light. And for these telescopes, as they get to be shorter, then those mirrors become more steeply curved. The more steeply curved mean that they have a more complex shape. Okay, the mirrors are near paraboloidal in shape. And so as a parabola gets a shorter radius, the departure from the sphere increases. Why does that matter? Because if you have a spherical surface, it's simple. Okay, a ball is really simple, but a piece of a sphere, the curvature is the same every place on it. Okay, so if you polish it, you have a tool that fits, it wants it to stay the same. Okay, and for measuring it, you have light that comes from a point source at the center of the sphere, it'll go back to a point at the center. As the mirror becomes less like a sphere, as it becomes more aspheric, the polishing and the testing get to be hard. And to make a mirror like this, the mirror surface has to be very good compared to fundamentally the wavelength of light or some fraction of a micron. The way you make anything with precision is you have to have the ability to change it, and you have to have the ability to know what it is. So if you think about, if I told you I wanted you to make a foot-long thing, 12 inches long, okay? Give me a board, cut it to 12 inches. What would you do? You'd get a ruler out, you'd mark it, you'd cut it off. Okay, the ruler is what defined the length. What if I said I wanted it to be 12.00000000 inches? You'd say, you'd look at your ruler and you'd say, I can't do that. Okay, how would you do it? You would have to come up with a better ruler that can measure, is it long compared to that or short compared to that? And then you would have some way to just file off the very end a little bit at a time, comparing it with your ruler. Doing that, you're making the thing based on the metrology. The metrology is the measurement. That's how all precision things are done. Okay, and that's actually how a lot of manufacturing things are done, is that it's the measurement. It's not just the check for what it is, it's the thing that defines what it is. You make it according to what the measurement is. Okay, so for these primary mirrors, that then becomes a challenge. You have to test them, you have to measure them so that you can make them. And this shows the same idea that I was saying a minute ago, that the aspect of the telescope has to change. This is actually a page out of my dissertation, which was on this topic here. This shows on a log scale here, the mirror size as a function of year, which is for the reasons I said. Get better images, get brighter images. But if you plot the aspheric departure on the log scale the same way, it's got a hook in it. Okay, this is years here. This hook is right where we were when I started this work. Okay, and to measure a mirror, you have to deal with the fact that it's not spherical. It's a complicated shape to measure. And so this background put me into the position where I was working on test systems for these mirrors. So how do you measure an aspheric mirror? Well, you start with an interferometer, because that's the only thing that we have that can measure surfaces with this kind of accuracy. And you can make an interferometer or buy one that makes a spherical wavefront that's very accurate. And then you put this thing in between here called a null corrector. The null corrector takes the spherical wavefront and with mirrors or lenses or holograms, converts that into a wavefront that'll propagate, and that wavefront will fit the shape of the mirror you want to test. Okay, if that's so, then that wavefront will reflect back on itself, back through the null corrector, back into the interferometer, and it'll give you straight line fringes. It'll look perfect. If there's a bump in this mirror, then the reflected wavefront will have that bump. It'll go back into the interferometer and you'll see a bump in the fringes. And you can measure that there's a bump there. You send the guy out with a polishing tool and he rubs it, measures it again and says, the bump has been fixed. That's kind of the game. So this is one of the first null correctors. This was the null corrector for the Vatican telescope primary that I showed you, the 1.8 meter primary 1988. So this has a little interferometer in the top. It has a couple of lenses. And so I was working on this as a student, did some optical analysis. I don't even remember what, but talking to Roger Angel about this, we needed to verify that this thing was right. Because if it's wrong, we might make the wrong mirror. And so my student project was to come up with this thing called a scanning pentaprism test that let us verify that the mirror is correct. The mirror itself is a paraboloid, okay? It's a parabola of revolution. And so there's this magic property of a parabola. If you send light rays that are parallel to the axis of that parabola, all of those rays will reflect to a perfect point at the focus of the paraboloid. So if you put a detector there and then have a system that scans those rays across, you can see if that spot stays in the same place, then it's a perfect paraboloid. If it's not, you measure the motion of the spot. Well, how do you scan some beam so its angle doesn't change? Here you use the magic of the pentaprism. Okay, the pentaprism is one of these special things that as the pentaprism rotates, it sends light in here, light comes out here. Or is it shown? Yeah, okay. As you rotate this pentaprism, this light will deviate a little bit, but its angle doesn't change. The pentaprism has two mirrors in it, so one of them causes a rotation, the other one causes an unrotation. And so if you scan this light, even though the pentaprism itself is moving along this rail because it's not perfect, the light doesn't change its angle. So the scanning system here lets me scan across the mirror, look with a camera at prime focus, at the paraboloidal focus, and measure if the mirror is right. This was my student project. At about the same time, the Hubble Space Telescope was launched. And this was a little bit bigger mirror, 2.4 meters, nowhere near as fast. And it was tested in Danbury, Connecticut by an interferometer with this kind of complicated null corrector that used mirrors instead of lenses. The null corrector I showed you used lenses, and the biggest uncertainty in that null corrector is the refractive index variation within that lens, because the glass isn't perfect. Nothing's perfect, okay? But with mirrors, you can measure their surface, and you can either back them out or you can always make them better. And so they built this incredibly accurate null corrector and polished the mirror with it. And they continued polishing. They developed computer control polishing until when they measured it, that mirror was good to, I don't know, 8 nanometers or something. Really fantastic. So this thing was launched and they expected diffraction limited quality out of it, but it did not achieve that. The first images are blurry. So you just change the focus, right? No, adjust the focus, they stay blurry. It's spherical aberration in there. How do you get spherical aberration in a telescope? Well, if your null corrector is wrong, then you'll polish the wrong surface. So the Hubble null corrector, it had these mirrors and it had some spacing rod that was used to set things up. There was some tiny error in setting up that spacing rod that caused that assembly to be incorrect, that caused them to polish the mirror based on that test. Until the test says the mirror is perfect. All right, they put it in the telescope, ship it, launch it, and see spherical aberration. So Roger Angel was on this Allen committee to go investigate this while I'm a student working on this pentaprism test back in Arizona. And I'm just a young whippersnapper kid. And so he would call me in the evening after the meetings and we would talk about different testing things. And I remember I did several analyses and sent them to him. There was not internet and email. We printed things out and sent it by fax. Okay, this is 1,000 years ago. So we had a solution for our mirror that we weren't going to have that problem, but the scanning pentaprism was pretty cumbersome and it wouldn't work other places. Enter Jim Wyant. So most of you, you certainly know about Jim Wyant. Everything's named from here. Hopefully you got to meet him. One of the many things that he did was to develop computer-generated holograms for optical testing. And he wrote a landmark paper on this that describes the basic elements of this. And so the gist of it is that you can create a hologram. You can design something in the computer that you can then write as a planar thing, and it'll diffract light in a way that you can use as a reference for measuring things. But wait a minute, how's it all work? Holograms. Do you believe holograms? So again, I was a student. I was taking Ray Kostick's class in holography, and holograms were just this giant tangled up mess of math. I did not understand how to do this. But Jim Wyatt's paper was really clear and obvious in retrospect that for this special case of these holograms that we use for optical testing, the holograms themselves, whether you calculate them with a whole bunch of Fourier math or if you just use simple geometry, they just look like contours. They're just curved lines that locally look like a diffraction grating. They are a diffraction grating. They're a binary diffraction grating, binary meaning two levels. Okay, so you don't need a whole bunch of math to do that. So it's a two-level grating. It diffracts light just using a vector form of the grating equation, which is pretty darn simple. So once I learned that, I'm like, this null corrector problem, there's an easy solution. So normally the null corrector is up in some tower that looks down at the mirror. So this is one of the null correctors for one of our telescopes. There's a simple idea is you just put a computer-generated hologram right here that diffracts the light back into the null corrector exactly in the way a perfect primary mirror would reflect the light if it was all the way down at the right place. And you can see how this works quite simply. Each of these rays goes back on itself. Okay, that's the litro configuration for a grating. And just using the grating equation, you can say, all right, if I'm going to make a hologram that's just a bunch of rings, my line spacing here, I can determine by what this angle is that I need. That's all you need. You don't need a whole bunch of messy math. Okay, you need to do this right, but it turns out it's very straightforward. It's easy to understand, and you would think easy to make. All you have to do is make a bunch of rings. But the way it works is each ring here corresponds to one wave of phase, okay, if it's used at the first order of diffraction. That's how it works. When you go back to your derivation of the grating equation, you just look at your vectors and you say, all right, this is the angle that one wave here at this angle, you get one wave per line in your grating, okay? So what that means is if you have a shift in one of these that's a quarter of the spacing, that you'll get a quarter of a wave of error. Okay, that makes kind of sense, but we need to get things that are good to sort of the 20th wave. So that means this pattern needs to be really good. Fortunately, other people had picked this stuff up. Jim Wyatt, his early work in computer-generated holograms, he developed the math. He had some prototypes. None of them worked, okay? Not that they didn't work. They didn't work to the level that was required because the ability to make the patterns wasn't yet there. But when I had this figured out, we were able to go to Steve Arnold, who worked at this company, APA Optics, then, who had figured out how to use electron beam lithography to make patterns onto glass that have much higher accuracy. Okay, he went on to found this company, Diffraction International. I'll talk about them in a little bit later. So I got holograms from him, and they basically worked. So this was one of the first measurements here. This is actually a grayscale of a phase measurement that let me measure that my null corrector, the error was only 11 nanometers RMS in the equivalent surface. Some of these holograms just didn't work. I had weird artifacts that would come up and talk to Steve Arnold about them, and the technology just wasn't quite there to do the things at the precision I needed to. You know where the technology was? This is a crazy thing. In Russia. So Tom Milster had met this guy at a conference who worked in Akademgorodok, which is a science city outside of Novosibirsk in the middle of Siberia. This guy came and gave a presentation on circular diffractive optics. Okay. And so this is Alexander Polishuk, who took over that lab later, but they have a circular laser writing machine, which is quite simple. That you put the substrate on, you spin the substrate, and then you expose the rings one at a time. If you have a very good rotation bearing, then you're going to have perfect circles. If you control the radial position of your exposing, then your lines will be right. Okay, and they came up with this really cool way to do this, which used, they call it the photochemical method. That used, rather than a photoresist or something, coat the surface with chrome and then hit it with laser light. That heats it up locally. Okay, it needs to be a small spot. That hot chrome oxidizes in the air, and that oxide acts as a mask. So then you can rinse away with sodium hydroxide the region that was not exposed by the laser, and then whatever was exposed by the laser stays there. And so you can make these ring patterns. And so I learned about them. I wrote a letter and sent it in the mail saying, hey, I'd like to come visit. This again was before the internet was regularly used. And I finally got a response and an invitation, and I went to visit this group in the middle of Siberia, in Novosibirsk. And I found out, yes, they really have this capability. And you know what? They're great guys. They're wonderful to work with. And so over, I don't know, the next 10 years or so, I probably went back there a half a dozen times and got holograms from them. And I got their senior scientist, this guy, Dr. Alexander Polishuk. I brought him back to the US, and he helped me develop some technology here for making our own computer-generated holograms. And so with these, we went on to make the primary mirror for the LBT, the Large Binocular Telescope. So if we look at the difficulty of making a mirror is proportional to how aspheric it is. So this one has 1.4 millimeters of aspheric departure, and it's axisymmetric. So we had a big null corrector that compensated that, and then we tested that with a hologram. It was about almost 10 inches in diameter, written by Alex Polishuk and his group. And that thing works, okay? The LBT telescope, it's only 3 hours east of here, and it's awesome, okay? This thing is on most nights, certainly all clear nights. And it works in 2 different modes. One is each of these is a telescope, and sometimes they have separate instruments on them. It also works in a combined mode. And so you get the interference between them. So you get the sensitivity of the full 23-meter baseline. And with that, one of the cool images that they made is an actual image of planets going around some other star. This isn't just some calculation based on wobble. This is actually an image that was made from the light from the LBT telescope. So this stuff works. I mentioned Alex Polishuk. He came back and helped me make our own laser writer. So they had a laser writer that wrote these little patterns that were accurate to some small fraction of a micron. The big telescopes needed big secondary mirrors. And I came up with this crazy idea of we could measure big secondary mirrors with a reference with a test plate that has a spherical surface on it. If we can draw onto that surface a hologram that compensates for the fact that the sphere does not match the asphere. Okay, so this was a crazy idea. At this point, I was a research scientist, I forget my title, working at the Mir laboratory. Okay, I worked there from 91 to 97, I think. And so maybe with the team there, we did a prototype. Working with Tom Milster, made a little hologram for measuring one of the secondary mirrors for the MMT telescope that I showed you earlier. That has a 6 1.8 meter telescopes. The secondary mirror from each of those is about this big. We made a prototype, and that worked. And so then we went to the university, and we said, the university has 7 telescopes, or needs 7 big secondary mirrors for university telescopes. And right now there's no way to test them, but we can do it. All right, what do you need? Well, we need to make the world's largest laser writing machine. All right, what's it look like? Sketch it out. And with Peter Stripmatter, we got funding from the university. We got a loan from the university to build the world's largest laser writing machine to make what was then the world's largest computer-generated hologram. This is what the thing looks like. So this is one of our substrates. This is the test plate for one of these big secondary mirrors. This thing rotates and we expose rings in it one at a time using the thermochemical technique that Alex Polishuk taught us. To develop these, this is a crazy thing. This takes 26 gallons of etchant of the acid, or it's a base that we pour into here. So normally when people think of lithography for things, they're things you pick up and you put them in a bath and you might spin it up to clean it or something. For these, we need a crane to move them, and we need a giant high bay area to be able to do everything with them. So I worked at the Mirror Laboratory doing stuff like this. I also worked on telescope instruments for these different telescopes, and again realized the joy that I get from working with a team. It's just what I love to do. While this was happening, I'm an employee there. I got a sailboat. So 6 hours due south from here is San Carlos, Mexico, which is on the Gulf of California. And it's a beautiful, beautiful place. And we would go camping down there. And I found this boat for sale. This is a 40-foot boat. It's called a Seawolf Ketch. And I bought this boat for about the same amount of money as my car. So it's not like a big, expensive boat. It's a big, difficult boat. Here's a picture of the boat where it was frequently in the yard with me fixing it. But this boat I kept down there for quite a few years. My kids grew up on the boat. Every summer we would spend 2 or 3 weeks aboard the boat. We'd sail the big trip across the sea to the Baja and go explore new places. It was just wonderful. I think that was probably one of the biggest things that kept me in Tucson, is that I had this incredible place that I could just go and be with my family. So around the same time, the James Webb Space Telescope was built. And this uses aspherical mirrors too. And I was on this committee they call the Product Integrity Team. And one of the roles here was to verify that the optics are correct. And so this is a 6-meter telescope. The primary mirror is made from segments, each one of which are about 1.4 meters in diameter, about this big. And the whole primary is an f1.25 near paraboloid. So each of these pieces has its own aspheric shape that comes about from being some piece of that parent. So these were measured using the new technique of, if you take your interferometer, instead of putting a hard null corrector in there, you have a diffractive null corrector. So I showed you how we use holograms to verify null correctors. Well, in some cases, you don't even need the hard null corrector or the lens mirror null corrector at all. You just put a computer-generated hologram in here. And this is designed, again, the same way. It's designed using the simple calculation of what's the phase that you need to be able to get the right shape. You don't have to go to a Fourier space and go back and forth for some complicated thing. And these holograms have multiple features in them. So there's what we call the null that's used to measure the surface, and then there are alignment patterns, one of which is a reflection pattern used to align the hologram to the interferometer. Other patterns are used to align the part to the wavefront. And so what was used for JWST was a set of spots that were projected, and there were targets mounted to the mirrors, and then you could find where those spots are with respect to the targets and then move things around until they're close enough. In this case, close enough was about 1/4 of a millimeter. This was all put together. It was used for measuring the mirrors for manufacture. They had a special difficulty for James Webb because it operates at 35 degrees Kelvin. The mirrors themselves are made out of beryllium. And if you take the beryllium, any real material, and you cool it, it distorts. Okay, we don't care what the thing is, what the mirror shape is at room temperature. We care what it is when it's making images at 35 Kelvin. And so NASA built this test set at in Huntsville, Alabama, to be able to put the mirror segments in, cool them down to 35 Kelvin, look through a window in the chamber with light that comes from the computer-generated hologram, align it, measure the shape cold, okay? Then warm it back up, see what that difference is. Now go polish in the difference, okay? So that these mirrors, when you measure them at ambient temperature, they did not look good. But when they were cold, they were. There's a lot of stuff that went into making that all work. We did only a few of these holograms. Most of these came from Steve Arnold at Diffraction International, the guy I talked about before. So the mirror segments were all made, put together. The telescope was put together. It was tested in a giant thermal vacuum chamber at Johnson Space Center outside of Huntsville. This was actually built for the Apollo tests. They refit this with a cryo shroud to be able to get it to 35 Kelvin. Built a bunch of optics up in the top to be able to test the primary. Those optics were all calibrated with holograms from our friends in Novosibirsk in Russia. And this is what the interferogram of this thing looks like when they measured it cold. And you might say, that's terrible. Look at all that. Well, this, when the mirror sits on its back like this has all of the gravity deflection. Okay, what matters is the shape of these mirrors when they're in space. And so what you see are the bumps due to the supports for these mirror segments. Put the mirror in space and voila. This does not look like our Hubble Space Telescope image that we saw before. This is fantastic. This was the first light image that was released from Hubble, from James Webb, and it's just fantastic. So it all basically works. So the next chapter in my career is I was working at the Mirror Laboratory doing this stuff and having a great time, thinking I never wanted to do anything else. And Stace Derniak wanted me to come to lunch with him, and I had interacted with Stace ever since we shared space in the infrared lab back in the 80s. And he said there was an opening in the optics department for a professor, and he thought I would be good at it. I'm like, maybe, but I'd love my job at the Mirror Lab. And I don't know, professor, isn't that a bunch of bull crap where you have to go to committees and you have to publish stuff? And I'm not into bull crap. And he told me, he said, it's actually really great. The bull crap is a small portion of it. He thinks I'll like it. He challenged me. And so I said, all right, I'll try it. And so I came on in 1997 as assistant professor with the idea that I'll prove to Stace that I'm right and he's wrong and I shouldn't be doing this. But there are some things that really entice me about the position. One is the whole aspect of teaching. So I love doing the research. We had students who worked there at the Mirror Lab, and I liked to work with them. And I had been taught by people, some of whom were fantastic, some of whom were terrible. And I felt like, I should figure out how to give back. What can I do to be a really good teacher to help people to learn, help students to grow, maybe is an important thing. So that gets me to Jim's thoughts about education. I'm up here, I can say what I want, right? So these are things that I think are important. And when I came into this position as a professor, I felt like these are important and I want to help further the things that I think are important. So first of all, the fundamentals. When you're learning things, the fundamentals are absolutely fundamental. And how many times have I taken a course where I go through all of this math, I pass the exam, I get an A, and I don't understand the fundamentals, okay? For you as students, get to the fundamentals, I would say. Work habits are critical. So curiosity, I think, is one of your best assets you can ever have. You know who learns the best? Who's best at learning? A little baby, okay, or a little toddler. Why is that toddler so good at learning? Because they're curious about everything. They're not afraid to ask the questions. If they see something that they don't understand or that surprises them, they're going to spend time to look at it. So for me, I think nurturing that curiosity is really important. And then critical thinking, just thinking through, what does this really mean? Okay, if you're doing something, why are you doing it? Another thing that I have a very biased, strongly biased in one direction view is that I think that you learn fundamentals. The other things you learn are skills. Skills are things that you can do once you've learned them. Kind of obvious, okay? But skills are always hands-on. The only way you can learn a skill is by doing it. I don't think there are many skills you could learn by thinking about them. You learn them by doing them. And if you have the right coach, you have the right feedback, the right environment, you can learn them really efficiently, but you learn them by doing them. And this is something I always told my kids, never, ever, ever let school interfere with your education. The world is so much bigger than what you're ever going to learn in your classes. Your classes are important because you're going to get the fundamentals. Yes, you need those. You need the skills. But the bigger world is actually, that's really, really important. And the last thing here is don't take yourself too seriously. Okay, you're here for so many years. If you do it right, you're going to have a good time. You're going to make an impact. The world will be better because of you. But it is what it is. So I moved into my faculty position, teaching classes. I taught classes in optomechanics, in optical systems engineering. I started a class in fabrication specifications, and there are some other ones, applied optics laboratory. I did several things with Matt Dubin, which I think were really great because I think Matt had such a fantastic idea about education, learning skills. So I had fun teaching classes, and I'm not going to talk more about that right now. I also led some research projects. So I was the faculty teamed up with Marty Valenti, who ran the optical engineering fabrication facility here. And the two of us, I think we were a real dynamic duo for doing some cool things. I wanted to push technology, and I wanted to get students involved all of the time. I wanted to see room for students to grow with their own projects and for them to experience the thing that I think is so great, is this joy of being part of a team doing something awesome. And so that was a mission of mine. And so some of the things we did, we built complete optical systems. The system here is on the Hobby Eberly telescope that's now operational as part of this Het deck experiment. This whole thing's like, I don't know, 8 feet tall. So we made the mirrors, we designed the mechanics, we built the whole thing. We aligned it with not one, not two, but 3 computer-generated holograms. It was a big project over quite a few years. Another one here, one of the later ones, was the primary mirror for what we call the Advanced Technology Solar Telescope, which now is the DKIS, the Daniel K. Inouye Solar Telescope. We did several 4-meter primary mirrors in the shop here. We had students involved in all kinds of different aspects, sometimes polishing, sometimes testing. The movie there that I showed is actually a hot wire in reflection. A hot wire was translated, it's up near the center of curvature. There's a thermal camera that looks at that hot wire, and then from the ensemble of images of that, you can calculate what the shape of the mirror is. Okay, now this is fantastic because this is done in the infrared, so at this point the mirror is not specular to visible light. It's still a ground glass surface. And so you remember the whole game of making something, you measure it, you change its shape. Well, polishing is slow, okay? Grinding is fast. And so if you can measure the surface while it's still in its rough shape, you can change it very quickly and efficiently. So we built all of the test equipment for that, made that primary mirror, and it's now in a telescope on Haleakala in Hawaii doing fantastic things. I maintained a connection to the mirror laboratory. I'm close friends with Roger Angel, and Roger always has crazy ideas. He had this crazy idea for what he called the 2020 telescope. He's like, well, 8-meter mirrors are easy. We solved that problem. We want 20-meter mirrors. And you know what? One of them's not enough. We need 2 of them that can move together like the LBT. Okay, but if they run in a track and we have combining optics that are separate, we could get a baseline of 100 meters okay, with telescopes that each have 20-meter apertures. This was a 2020 telescope. So I worked with Roger on that. The other crazy idea he had was the dark matter telescope. This was, if you take an 8-meter mirror and you put a big hole in it, you can send light through from the secondary to another mirror called the tertiary mirror, third mirror, primary, secondary, tertiary mirror, and then bring that to focus at f1.25 at a fast focal ratio through some lenses onto a huge focal plane, to a 3.5 gigapixel focal plane array. And with that, you can image the whole sky. And both of these are bat crazy. Nobody would ever do them, right? Well, kind of. So the 2020 telescope was de-scoped. Somebody said, let's build one first. And so that became the Giant Magellan Telescope. Okay, the Giant Magellan Telescope is, as Roger said, it's an array of, the primary mirror is an array of 8-meter mirrors. They together looked like a 20-meter mirror. And then that gives you this giant telescope. And I was asked, well, how could you measure such a thing? How could you measure these primary mirrors? So we go to our heritage. We made 8-meter mirrors. We made the LBT mirrors, for gosh sakes. The LBT mirrors were axisymmetric. The aspheric departure is 1.4 millimeters. GMT, if you look at one of these mirror segments, it's an off-axis piece of an f0.7 paraboloid. It has 14 millimeters of departure from sphere, and it's not axisymmetric. So yes, Roger is still crazy. So if Roger's crazy, I can be crazy. So he came up with what I call the mother of all null correctors. Okay, so what if we have an interferometer? Now we can't have a hologram or any single mirror. If we have an interferometer and a hologram and 2 mirrors, all those things in combination, they make the wavefront that propagates to fit that crazy 14 millimeter aspheric departure shape. That'll go back on itself. You can measure the mirror. This works perfectly in Zmax. So we said, what would it take to do it? First of all, a 4-meter mirror, that's bigger than most people's telescopes. And a mirror that big doesn't take the shape doesn't maintain its shape. So we looked at what it would take to do that. We put the 4-meter mirror in the top of the tower and then make it an active mirror so we can change its shape with actuators and then look at it while we're doing that from its center of curvature. It's a spherical mirror. Then we could make this work. So this is the mirror laboratory under the stadium. There's a cone there. Inside of that's the test tower that the LBT was done. And here's the test tower. We needed a bigger cone, and the athletic department says no. There's a club right outside of that we may not change. So we squeezed a bigger tower into the same exact space. And so this is what the new tower looks like. And this was then built in, I don't know, the early 2000s. I don't remember exactly. And these are some pictures of stuff inside of there. So this is a fisheye lens view that you can see up into the tower. This is the small optics assembly. And this is Michael Toll. If you know Michael, he's like this tall. He's a big guy. That has in it the interferometer. It has not 1, but 2 holograms. And this other mirror, this 70 centimeter mirror that's used as a reflector. What we call the fold sphere, that 4-meter mirror, it hangs at the top of the tower, face down. So we're back to Hubble, aren't we? We made the mother of all null correctors. Well, we also made the mother of all scanning pentaprism tests, okay? But this now has a new complication. The mirror is nearly paraboloidal, but its axis isn't on the mirror. Its axis is off to the side. So that means that our magic pentaprism is going to scan in some angled space. Okay, well, it's just geometry. You can always make it work in Zmax or on the computer. So we built this thing. That's what it looks like. So to measure the whole thing, there are these rails. This plane is tilted by the amount that the axis is tilted there. And then the rail rotates to be able to sample multiple slices across there. And yeah, this is a picture of what that hardware looks like. And so this has now been operational at the Mirror Lab for 15 years anyway. And I don't know if all the mirrors are done. Daewoo can probably give us a status. How many?
4 is done.
So four are all the way finished, and all the other ones are started in some phase, I
And
think.
3 exists
Okay.
in the lab.
Okay. So Roger's not so crazy. Okay. All of these things are coming together. The telescope itself is being built on a mountaintop in Chile. All of that stuff moved forward. The dark matter telescope, that became the Large Synoptic Survey Telescope, which became the VC Rubin Observatory, which was basically very similar to what Roger laid out in the first place. It's a wide field telescope. The primary mirror is 8 meters in diameter. The tertiary mirror is actually made onto the same piece of glass as the primary. So this is one piece of glass with an outside region that's the primary, an inside region that's the tertiary. There are these giant lenses that initially that was thought to be impractical to make a lens that's this big. It's this thick, and it has to have really high performance. They're steeply curved and aspheric. All of those things have moved forward. This shows the polishing of the primary mirror and the tertiary mirror at the mirror laboratory. So there's a computer controlled polishing machine. Daewoo did a bunch of the work for this. There's a polisher here on this outer region that's tertiary. The inner region is, the outer region is the primary. The inner region is the third mirror, the tertiary. So those were polished. How were they measured? You know it, computer generated holograms from Russia. So the primary mirror, it was measured with a null corrector that was the LBT null corrector, changed some, okay, because the prescription was different. And then it was calibrated by a hologram from Russia. The tertiary mirror, it was small enough that it could be measured by a hologram. We didn't need other lenses or mirrors. But then how do you know the hologram's right? Well, you need to calibrate it with another hologram. So another hologram from Russia. And that test was the coolest one because here we had a computer-generated hologram null corrector, which is practically perfect, okay? Calibrated by a computer-generated hologram master that's practically perfect. And you look at the wavefront and it looks like something out of a simulation. It just looks too perfect. The lenses were made by Arizona Optical Systems, which is a company that Marty Valenti and I started from our work here. We did all of the grinding and polishing of these lenses. The lenses were measured with computer-generated holograms and aligned with computer-generated holograms, and the transmitted wavefront through the system was measured with computer-generated holograms. And holy moly, does this telescope work? Okay, if you watch any news or something in the past month or so, you keep seeing things about the Vera telescope is finding all of these new, the Vera Rubin telescope's finding all of these new things. So that was, again, one of Roger Angel's crazy ideas it's not so crazy. Back to my role in optics. So some other things we did, so I had some funded research projects. This is the normal model for faculty at a university, is you get funding not so much to make things that somebody's going to use, you get funding to develop technology or to do research. And I did some of that. We developed some testing techniques. We made some space optics prototypes. I'd have to say those things were fun. I really enjoyed being able to pursue some things that I wouldn't have been able to pursue without funding. But I learned an important lesson with this, which is if I don't have a deliverable at the end of the day, it's hard for me to be productive. Okay, I need to somehow create a sense of urgency, not just for me, but for my team, to be able to get real things done. And that's just what it takes. If it's just, oh, we'll work on it until we're done, it's not going to work. But we ended up getting some really cool things done. And it was part of the fun stuff that I did here. We also made some very interesting things. We had fantastic capabilities, engineering and manufacturing. We made the test optics for this Kepler Space Telescope, which was used to find exosolar planets. We made a bunch of convex off-axis parabolas, 1.4 meters in diameter, that are accurate to, I don't know, 12 nanometers or something. To do that, we built a whole new testing technique. We did some other things that were, because we had the capability, we made a 9-foot diameter, 2.7 meter flat mirror, and articulating stages, and an in situ measurement system, which is a subaperture scanning system. The subapertures were 1.4 meters. Scan it, stitch it together to be able to calibrate that mirror in situ to 3 nanometers. Okay, this took 5 years and $1.5 or $15 million. I can't show you any pictures of it because this stupid project was restricted. And this is one of the things that drove me crazy here. Because this is really pushing the state of the art. And because of some of the rules that were in place, the project, this flat mirror, was used to calibrate something else that was used for space. And so we could never publish anything about it. So that was very unfortunate. So that was me as a professor. So now we'll have an intermission. In 2017, my son and I got our boat out. We spent months preparing. This is the sailboat here, the Akela. It's mostly wood, an old school sailboat. At that time, the boat was in San Diego. We waved goodbye to San Diego, and we head off into the South Pacific. Okay, to see where we went, we have to zoom out a little bit. This is the Pacific Ocean, right? It's really big. Right in the middle of the Pacific Ocean is a country, French Polynesia. There are hundreds of islands. There's this island group up here called the Marquesas. It's about 3,000 miles to sail here from San Diego. So we sailed from San Diego to the Marquesas into Taiohae Bay. This is where Melville jumped ship from. Okay, we were there. We spent some time there. We went to this other island group. These are called the Tuamotu Islands. This one we're actually at for months. These are crazy islands because it's like it's out in the middle of the ocean. There are these rings. It's called an atoll. Inside the ring is like this lake that's 100 feet deep or so. Went to Tahiti. Tahiti is, if you've been to Hawaii, it's similar to Hawaii, but it's much, much less developed. There are people who live around the outside. These islands here are called the Leeward Group. The famous one you maybe have heard of is Bora Bora. We went there and you see there's lots of civilization there. And if you zoom in, you see there are these fancy huts on the water. And so we would sit there on our boat, anchored, looking at people, looking at us. And you know, they're spending $1,000 a night to be there. And we're living on our boat there for around here for almost 3 years, paying basically just buying food. So that was really cool. So this is what it looks like coming into the Marquesas. It's lush and green, and there is nothing like the smell of the earth when you've been at sea for 3 weeks. I can guarantee you that. So what was it like to be there? Well, we live on a boat. For us to go ashore, we'd anchor the boat. We have a little boat that we would row in, take it to the beach, and maybe go find food, go talk to people. We had paddle boards that we used to get on and off the boat. Spent a lot of time in the water. The places we were, oh my gosh, they're just rich with sea life. And a lot of the places we were that nobody else can get to. We were literally diving, scuba diving one place, and we see somebody with this big rig, and he's there from National Geographic. He wants to film this particular thing because it's really cool. And we just happened to be there. We caught and ate lots of fish. I got good at spear fishing. And we spent a lot of time just hanging out. The weather there is like perfect year round. It's a nice place to be. We spent time with the locals. Oh, that's cool. So we met a lot of local people, and they have their festivals. We go to the festivals and just begin to watch them. So that was kind of fun. The experience of being in someplace where it's really difficult for regular people to get to and to have time to be there, it was phenomenal. It wasn't just me. I sailed there with my son Max, and then we had, over the time we were there, we had a lot of people who would come out, sometimes for a week. Dave Wook and his family came out for a week, sometimes for 3 months. I had friends who came and lived with us on the boat. My wife Laura came out a number of times, and the whole experience was just so rich, and I'd never trade it for anything. But I had to come home. Coming home, it turns out, is really hard. Because it's so nice to be there, right? And you never want to leave. Well, yeah, but it's also, if you look at this movie here, this is a sequence here over a week. So it shows how the storms and things move. You see, these are the trade winds blowing this way. They always blow that way, okay? And so when we're here, it was easy for us to get there because we ran downwind. For us to get back, we have to go against those winds. And so that's really hard to do. You can do it in a sailboat, you have to tack, but it's hard, it takes a long time. So we went from Tahiti, we went back to the Marquesas. That's about 1,000 miles. Then we went from Marquesas to Hawaii. That took about 3 weeks. That crosses this region here that's called the Intertropical Convergence Zone, the doldrums. In that region, there's no characteristic wind. There's nothing but storms, and you may get one. It may be terrible, or you may get none. It's crazy. The storms will just pop up and blow like crazy, and they'll be gone in an hour. But you get through it. Sailing from Hawaii, we can't just sail straight against the wind, so we go way north. We go up north to where the westerlies come in, and they push us back around. That trip, because we had to go so far north, took 4 weeks. It was 28 days at sea. Okay, and now back to our regularly scheduled programming. After that, I came back and I'd left the university. Chen-Yu and I had founded this company, Arizona Optical Metrology, in 2009, and we decided that we would ramp this up. So it was just he and I. We did single holograms for people based on what we had done at the University of Arizona. So we put in place the ability to make not just holograms, but test systems. And so we have a facility, we hired people, we have products. So these are some of our holograms, and we do the design, the E-beam or laser writing, we subcontract, and then we do all the processing after that. And we've done a lot of these. So we have this software called Jira that we use for tracking things. So since we've been using Jira, we've done 1,242 holograms, okay? That's a lot. Currently, just right today, or when I took this a couple of days ago, we have current orders of 29 holograms, 16 metrology kits, engineering services for 8 things, and 5 full test things. These are things we're actively working on right now. We have so many things going on, okay? And it's a completely different. At the university, we had one project that would go for 2 or 3 years, okay? Here we have, at any one day, 30 projects going on. How do you do that? You don't do it yourself. So this was a big lesson for me. I don't expect you to see any of these details, but this is our structure. This is what it takes to run a company that does everything you need to be able to get the business, to make things, to ship them out. Each of these boxes, this is an engineering box. There's somebody who has to take that responsibility, okay? And so we started with a blank piece of paper, so we're like, we're going to do this right. We were lucky to have Jake Beveridge, who was an organized guy, and he set up much of this stuff. I want to point something out here, is that all of these boxes are roles that need to be filled. They're not necessarily individual people. These are things that we have to have specifically assigned to somebody, and lots of people have several assignments. But if you look at all this, you see that there's just one box here, optical engineering. Say computer generated holograms, I could do that, I'm an optical engineer. Yes, you probably could. But I can tell you, if you want to run a company, there's a whole lot more that you're going to have to do. I'm not complaining. I like it, but there is just a whole lot more. So the CGHs, they're simple structures. They're planar, meaning that it's lithographed pattern on a surface. If you look at it up close, it'll look like a bunch of lines. And this is something that I think is just a gift from nature, that we can, in our computer, figure out how to take a structure that's in a plane, combine that with light, and we know the physics of light, and that's going to give us a wavefront that's a three-dimensional shape. Okay, we can put a wavefront in space that's actually more accurate than any surface that you can make. It becomes the master for making things. Okay, and I don't know, I just think that's really cool, the fact that that is possible. So what's a CGH look like? It's on a single substrate. There will be multiple patterns, perhaps some used for alignment. If you blow this up, you'll see that the lines themselves aren't smooth, continuous lines. They're a bunch of little line segments. Why do we do that? Because there's already this fantastic infrastructure for making little line segments. Okay, that these are photomasks. Every single integrated circuit that's made will have a number of layers that are exposed and then processed into the silicon. Each of those layers is defined by a photomask that gets imaged onto there. That photomask is written by some e-beam or laser writer. And that infrastructure is already there. So what we need to do is have them write onto our substrates, write our patterns, and then we do the processing from there. They also have fantastic quality control. If you're building up an integrated circuit with 100 layers in it and one of them's wrong and you don't know it, you might lose your whole thing, which you just can't afford to do. And so every single hologram that we make goes into a second machine called iPro, and that machine measures the distortion. So this is data out of one of these things. This measures the actual pattern, how much that pattern has been distorted. And this is good to around 10 nanometers or so. Okay, and then that coupled with diffraction lets us control the wavefront to an accuracy of about 1,000th of a wave. And we have bulletproof quality control. You don't just have to take our word, you can see what this other machine measured it to be. So the modern computer-generated holograms, we can make pretty much any wavefront, practically perfect, and coupled with interferometry, we can measure all kinds of things in a snapshot. And this is another gift, I think, that one gift is that planar things can make three-dimensional things. The other is that we're here at the right place at the right time, that the photomask capability is there. We don't have to develop it. So something AOM has done is to take computer-generated holograms and build them into systems that are more easily used by a variety of people. So we have the hologram that creates the null wavefront for measuring the surface, but we also have multiple alignment patterns that we send the alignment patterns out, and they're used for setting up the test and making sure the part's in the right place. I have a couple of movies of this. So this is one of those alignment patterns. It shows that it's coming to focus here on this corner cube. Okay, the corner cube is fixed relative to the part. So once you move that until it's visibly there, then you look in the interferometer and you see these fringes. Okay, and these fringes come from the light that's reflected back from the corner cube, and they tell us the position. If that corner cube is shifted, then if it's shifted in this direction, then we'd see the arrows that point this way. This is just using simple geometric optics to be able to do that. And then we build these into more and more complicated systems. So we can provide the hologram, the mount for the part, the alignment stuff. In some cases, the part just clips in kinematically, and then we make a snapshot measurement. We do holograms for measuring systems as well as surfaces. So lots of times systems are made in two separate parts or several separate parts. Each part is not corrected, but you can then create a wavefront from a hologram that lets you measure the one part of it separately from the other part, and then when they're combined, they'll work correctly. So that's a area of business for us. And then we build these into test systems. And so we make test systems for, right now we have 4 different projects at different stages making test equipment for space telescopes. Okay, we're not just doing the hologram, we're doing the mounts and the alignment gear and all of that stuff. That's kind of cool. Yeah, and I mentioned this, so if we have a part, I can't show you the customer's part, but you can imagine it has some datum feature that's going to sit down uniquely onto this thing. This is our metrology platform. The metrology platform has reference optical features on it that define the position with respect to the mounting features for the lens. That whole thing is set up so when the part gets installed here, this thing can just be clipped on using kinematics and there's no alignment. So it lets a snapshot measurement. So these get built into systems that then are loaded by robots and can be measured very, very efficiently. That's a big part of our business. Okay, so back to the students. Jim's plea to the students. Learn the fundamentals. Your work habits, they're going to live with you for the rest of your life. And I talked about those things already. Getting experience. So if there's ever a lab class you can take it. If somebody's doing something and you don't know why they're doing it or what they're doing, if it has to do with optics, have them explain it to you. Okay, get hands-on experience with things. You're going to learn by doing, okay, whatever it is. Pay attention. There are free gifts in the world. Okay, you can get them if you want, if you pay attention. Something I learned is to get something done, you have to have some sense of urgency. Why am I doing it? And I need to define, if nobody else for a timeline, I need to create it. Something that I've learned is you have to know your values. What's important to you? Okay, and sometimes it takes stopping, thinking about it, and then maybe making a hard choice. But at the end of the day, you live by your values, you'll be really glad you did. And the last thing is just never take yourself too seriously. So, thank you. Any questions? Yeah.
But you can still collaborate with Novus and Beers?
So no, the Ukraine war shut that down. So it's illegal to work with them, which is unfortunate because, I have this very negative feeling towards Russia as a country because what they're doing is crappy. However, these are my friends, okay, who work there and they're not doing it. And I would love to be able to work with them, but it's not possible right now. Will we again? I don't know. Yeah, that's sad.
Yeah.
It's really sad. Yeah, Alex Polishuk, I showed you, he came here and he stayed with us and he had dinner with me and my family often. I spent time in Russia. The first time I went there, I was not only the first American, I was the first Western person that most of the people that I interacted with had ever met. Okay, this is in the middle of Siberia, it's tucked away. So I have a special fondness for these people, and it's very sad that there's a political problem.
You still have a boat?
Yes, I do still have the boat. The boat is in San Diego, and I was there just 2 weekends ago fixing my anchor windlass. I spend way more time maintaining the boat than sailing it now. Someday I'll go offshore again, but I don't have any specific plans.
When is the next New Year's trip?
So one of the things I did with my friends who I boated with is we rented a boat in Croatia for 2 weeks. We did that a couple years ago and that was fun. They're trying to talk me into doing a trip in Greece, which maybe we'll do in May. Other than that, I don't know. You want to go sail with me sometime?
Let's talk about it.
Yeah.
Thank you. Great talk. And it sounds like the CGH is already quasi-perfect or near perfection, according to what you said. So what's left? Or is it already done until some new magic comes out? What's your view?
Yeah, the CGH is there's a production of photomasks. There's a knee in the curve for everything. Okay, so we can get really good production photomasks at a good cost and good schedule, but they're not the best that could possibly get. And so what we do is we have special substrates, we get the photomasks that have the right affordability, and then we calibrate out any errors that are. So those things could always get better. There's the size. So 6 inches, easy standard. We now have 9-inch as a standard. That's pretty big. We have current plans to go to 12-inch and create that as standard. We have done bigger ones, but when they're special, as a business, they're a bad idea. As a student or a university, if they're special, hot damn, yes, that's what you want, right? As a company, no. Anything that's special means you're going to lose money, and that's okay. You can lose some money if you make it up other places. So where our business growth hasn't been in new holograms, it's been combining them with other equipment. Okay, to be able to use the hologram in combination with other things for measuring alignment of other things.
So one additional quick question. Why binary or amplitude holograms can be really good? What about other like binary phase or even non-binary? Are they also really good?
So the complexity of the hologram drives the cost. The simplest hologram is just a chrome pattern on glass, and you can use that in reflection or transmission. And you get 10% diffraction efficiency or so, which is fine for some things. If you need higher diffraction efficiency, then we can etch that pattern into the glass, then strip the chrome, then it becomes what we call a phase pattern. Okay, and that can get to about 30% diffraction efficiency. We can also do multi-level ones, where there's one that's etched, and then there's another one that's etched on top of that, so we can do a 4-level. Each time we add a process, we add cost and time and complexity. And so we don't, again, as a business, we don't like to do that. We want to choose the simplest solution.
Thank you.
Who makes the holograms?
So the holograms are written by one of several mask houses. CompuGraphics, there's a company that used to be called Topan, Photronics. So these are companies that their business is photomasks for integrated circuit production. So we work with their engineers to be able to tailor their process for what we're doing. And then we provide them a graphics file that has all of these tiny little polygons in it. And then they do the writing, and then we do all the processing after that.
And like, how many holograms do you have to order to work with them? Like, as integrated circuits, it's a problem to scale, right? Like if you're buying a bunch of holograms, that company will do business with you, but if you had a specialty hologram.
I don't know the answer to that question, but the photomasks are all unique. So we're never writing the same thing over and over. But our history, we started this in 2009 when we maybe did one a month or something. Okay, and it's the same supply chain, same group of people that did the writing. So if you work out a relationship where you know how to spec the things that they can do with their existing capabilities, then you could just do one. Yeah.
This might be a bit of a naive question, but I'm just wondering, how come people don't just forego the null corrector and use like a flat base front to do interferometry and then computationally reconstruct the surface of whatever test subject you're trying to measure?
Yeah, so the dynamic range of the measurement you would never see anything except a tiny little region. And
I guess
there are people who
like in terms of like the cross section of the test subject or the depth dynamic range of like the deviation of the surface from the intended shape, or you mean like
so the way the interferometer works is, or any phase sensor, is it has some range that it can accept. Okay, and if you go outside of that range, you don't see anything. So if you take an interferometer, a plain interferometer, and you stick it up to measure one of these mirrors, there's just going to be a tiny little region that actually even makes it back into the interferometer. So you have to do something. Now, there is a technique for using that. They call it the plane wave interferometer, where you measure these tiny little regions and you move your system around and then you stitch it all together. So it's possible to do that. And if you get everything right, you can do it accurately. Okay, what we provide is is two things. One's it's a snapshot measurement, a hologram, and the other is you don't have to do anything to see if you got it right. We already have the QC built into.
Makes sense. Thank you.
How much phase period you can measure using CG?
It's so a typical amount of aspheric departure is a few hundred microns for some parts sort of in this range. Some of them go to a few thousand microns. Once it's more than that, usually we need some other geometry, some other thing. And it doesn't matter if it's axisymmetric or freeform or what. Because it's all, if we can model it, we can model the wavefront. If we model the wavefront, we can create the wavefront.
I'm not an optics person, so this might be like a dumb question, but how are like the patterns with holograms derived? Like how do you get the pattern that you have to write on something?
So the simple answer is it comes from a computer model that defines how the diffraction will work. So the way diffraction works is light hits the structure and then it scatters off in different ways. Okay, there's some simplifications in those models that make it easy, but it's all in software to be able to do that. So the design of the test is first to design the optical portion to say, this is what I want the light to do. At this point, you're not defining a hologram yet. You're not defining the structure. You're saying, I want the thing that will cause light to go this way. This is all done in ZMAX or Code 5. These are optical design programs. Okay, once you have that, then it's a totally different step to say, what's the structure that would cause that diffraction? So there we use the rules of physics, and we have some pretty darn sophisticated software to efficiently create. We have several billion little polygons in each of these holograms. Each of them has to be right. So we have some software that's pretty highly optimized for that task. Sorry, I could tell you more. It's not that I'm not, because it's a secret. It's that it takes more than a short answer. Yeah.
Can you touch on how you do alignment with the CGH?
Well, it depends. So the thing about the CGH is we can write into the substrate onto the single part any pattern we want. And so what we do is we write multiple patterns on, and we use those in different ways to set alignment. And so what the patterns are and what we do kind of depends on what's going on. So the easy one I showed there is to be able to set the hologram with respect to the interferometer. There's a reflection pattern that goes back into the interferometer. That when the hologram's in the right place, you measure that it's in the right place. For the other things, it sort of depends on where it is, how far it is, and which thing we're going to use. So the easy one is if we send light to a focus, you look with put a card there, and you see, is that focused in the right place with respect to the edge of my optic? Okay, you can do that just visually. If you want to do that to something to a tighter tolerance, you have to put something else there than a card. So what can you put? You can put a ball. That's a common thing, as a sphere. If you know where the sphere is with respect to your optic, then we can measure where the sphere is using a special pattern on the hologram. And then you set the thing up that way. I don't know if that answers your question. There's not an easy answer because there are all kinds of different tricks for this.
Oh, yeah.
Yeah.
So it was a great and your patient for the mirrors was impressive, but how about lenses? Like there are many like freeform lenses and there are many proposals for that. So in that case, what is the challenges and how can we use the CGH for that?
Yeah, so the CGH interferometry just measures the surface. And so if it's on a lens or a mirror, we don't care. So I would say a lot of our tests at AOM are for lenses. So we just measure the surface. There is potentially the reflection from the backside of the lens that we have to be careful, because if we get a ghost, it'll affect the measurement. Otherwise, it's just a surface. Yeah.
How high precision is the manufacturing of the hologram and the holograms made on the glass surface or sphere or freeform surface?
So the substrates for the holograms are plain. They're plain parallel plates. Okay, and they're polished really good. So there's very little wedge in there, and the surfaces are practically perfect. And so we put the hologram on one of those surfaces, and then we'll put an anti-reflective coating on the other surface. And I'm sorry, I missed the first part of your question.
And how high is the precision of it?
So the precision of the pattern internally is good to about 10 nanometers in plane. Okay, meaning that a feature is in the correct place with respect to the other features, because they're all written at the same time, with an accuracy of about 10 nanometers. That's the knee in the curve. Okay, we can go to 2 nanometers, but the cost goes up by a factor of 4. And so we never do that. Okay. Yeah.
Mentioned you measured the accuracy of a CGH with another CGH.
Mhm.
How is that done again?
Well, I can sketch it for you. So the interferometers here. This is what the test is supposed to look like. Okay, so this is the interferometer, it sends light out. This is the CGH that's used to measure this mirror. Okay, so all we do then is we make a different CGH that we put in here. And we design this CGH so that this light will be reflected back. So there's no mirror here when we do this. So we're testing this wavefront created by this. So that lets us measure a CGH by a different CGH. And it's manufactured differently and the models are different. This CGH is really interesting here. This CGH is defined only by this mirror. Okay, it's defined, if you look at what this mirror is, I'm going to way too soon. The mirror has some shape. Okay, the wavefront or the rays that will reflect back on themselves are normal to that shape. So this wavefront is uniquely defined. And so this hologram, what we want to do is make this surface here such that these rays would reflect back on themselves if they fit the shape of this. So designing this hologram, we don't ever look at this. We don't care what's testing it. Okay, and so it gives some independence to those two things. Best test ever.
Adapting the laser etching process from your Russian friends to a spherical test plate, did that work right out of the box? Or what went wrong?
With the big writing machine,
Mhm.
that took years. I mean, it probably was 2 full years from the prototype to us doing a test with that. What are some interesting lessons learned? We couldn't afford the laser we wanted, so we bought a used one. That was a terrible mistake. We spent a lot of time dealing with problems with the laser that I never knew would have. We had this very high frequency oscillation that would come and go. This laser writer was pretty sophisticated because you can't just focus a beam and rotate this thing, because if you put enough power in there, it was burn the chrome off. So we have a acousto-optic modulator that takes the laser beam, focuses onto a really narrow spot, and then scans the thing while it's moving underneath. Okay, and so there's a lot of sophistication to enable that whole thing to work. Well, then we had interaction between the dynamics of our scanning and the stupid problems with the lasers that were not stable. And we spent more making that laser work than it would have been to just buy the right laser. Other lessons learned, I'm not sure. Complexity will bite you in ways you didn't expect. That's every time you do something, you relearn that lesson. In the end, it all worked as it was supposed to. And we made holograms for us. We made holograms for industry. A number of other people's telescopes were measured with our holograms. Once I left there and there wasn't a demand for the big convex mirrors, nobody used that for a while and that capability's all gone away. You have one or you're limiting to one?
Yeah, limited one.
Okay.
Thank you for the presentation. I had I guess more of a conceptual question. So say you're designing a new precision instrument for metrology, and you spec, like for instance for CGH, we can measure the depth deformation of a surface up to like 2 nanometer precision. How do you verify that that's an accurate claim without having an instrument that's more sensitive, let's say? Or do you just base it based on like the physics of the design?
So two things. One is for the particular one, you just have to base it on your quality control. That each piece is not, it's either physics like the wavelength of the light. Okay, we know that the Heaney is going to have this transition. Or that there's a specific quality control that measured that aspect is correct. Okay. And then that's the best we can do. And that provides, it's totally traceable, but only in steps, which isn't all the way satisfying. And then the other is validation that you've done that correctly by using the same process, the same analysis for some other test that you can verify. And so that we did a lot of. And so that lets us verify the process. But still, there's always this tiny bit of doubt. If you can't prove that everything's right, you don't know for sure that it is. So you can establish some probability, but it's the best we can do. But we do have really good QC for each of the steps. Okay.
So let's thank Jim again. Thank you, Jim.